Hello, everyone. Welcome to the final presentation for the Internet Equity Initiative, where we'll share with you some of our work that we have completed throughout the quarter. Looking at our agenda, our presentation will begin with an overview of our project to provide more context on what we were doing. Then we'll move on to what we have learned from our Milwaukee data, which will be our section throughput performance, last mile latency, and ping test. Then we'll wrap everything off with our conclusions for the project. So beginning with an overview of our project. On our team, we have Alexis Schroep, the IEI director, as our external mentor. And we also have Jonatas Marquez, a DSI postdoc, as our internal mentor. Stellton was our TA. As for the students, we have myself, Cissy, and Jack, Hannah, and Alexa. We're all undergraduate students at the University of Chicago. So moving on to the project background, the IEI's goal is to provide equitable, resilient, and sustainable internet solutions to benefit all communities. But what does that mean and why does that matter? The mission of the IEI matters because even today, persistent inequalities exist within internet access. For example, according to the IEI, at the start of the COVID-19 pandemic, more than 110,000 children under the age of 18 in Chicago did not have access to broadband internet connectivity. This is detrimental to our society as more people depend on internet connections for education, work, socialization, healthcare, and more. Therefore, many policymakers are attempting to remedy this inequality, and is where the work of the IEI comes in, as we provide problem-driven measurements, data and analysis, models to evaluate diverse connectivity options, and research on the social effects of infrastructure investments. As for our project goals this quarter, our main goals are twofold. Firstly, we want to analyze broadband data in Milwaukee, where we process data collected from 55 household devices in Milwaukee and produce good documentation of data through a data dictionary. Secondly, we also want to write replicable code for future data analysis. In this case, this will be generating a query formatted PDF report, and the code we produce should be reusable for data collected on IEI's devices in the future and reduce manual labor for researchers in the process.
Now we will begin to talk about the report. The first section focuses on throughput, which is the amount of data traveling successfully across a network. Devices used the Ookla Speed Test and Measurement Lab's NDT7 tool to run upload and download speed measurements. This helps us gauge throughput, as faster upload and download speeds indicate higher overall throughput. 25 down, 3 up megabits per second is the minimum broadband download-upload speed benchmark set by the Federal Communications Commission, or the FCC, in 2015. In 2024, the FCC voted to increase the benchmark to 100 down, 20 up megabits per second. These benchmarks are used to assess the deployment of broadband across the United States and to determine how the FCC measures progress against funding requirements set by Congress and the states. Out of the 55 Milwaukee households, 34 reported median throughput speeds below that 100 down, 20 up megabits per second threshold. This accounts for approximately 62% of the total household sampled. The box plot on the right shows device download distributions for the Ookla Speed Test for Milwaukee devices sorted by median. The download benchmarks of 25 and 100 megabits per second are shaded for ease of identifying which devices fall below which thresholds. Given the length of the box for the highlighted device, we can deduce high variability in download speeds for that device. Normalized reduction captures how a throughput measurement varies. In this table, devices are sorted by normalized reduction index, where NR index is the average of Ookla and NDT7 upload and download speeds. Essentially, it is the average of all the columns to its left. Lower numbers indicate more consistent performance, and higher numbers indicate more severe degradations. Only the last 17 rows of the normalized reduction table for Milwaukee devices are shown for space and to highlight the functionality of the heat map, where darker values coincide with the larger normalized reduction measurements, indicating overall worse user experience. We can identify the same device as from the last slide highlighted in the table. Its position near the end of the table makes sense, given the box plot also captured high variability for that device.
So last mile latency refers to the performance of the final segment of the network that connects an end user's device to their internet service provider. This metric provides insight into how well the provider's infrastructure is provisioned, with lower latency numbers indicating better performance. Here, we're using the trace-through test, which examines the entire network path to identify latency across multiple hops, including the last mile. For this analysis, I processed data using the results function to retrieve latency measurements. The left graph illustrates variability in maximum latency across devices, and the right graph highlights extreme latency spikes and outliers in maximum latency measurements. A threshold of 100 milliseconds, defined by the FCC as the maximum acceptable latency for broadband connections, was used to classify devices with acceptable or poor last mile latency. Half of the devices show stable last mile connectivity, with latency values consistently below the 100 milliseconds threshold. This indicates reliable performance for most users in non-latency sensitive applications. However, 45% of devices recorded maximum latency values exceeding the 100 milliseconds threshold. These connections are not considered broadband under FCC guidelines and are likely to face challenges in real-time applications such as gaming or video conferencing. Based on this result, 24 devices were identified as exhibiting poor last mile latency, with some showing extreme latency spikes. Certain outliers exceeded 2000 milliseconds, as shown in the right-hand graph. Latency performance varies significantly across devices, and while some devices maintain consistent low latency, others display large variability or extreme outliers, as represented by box plots. However, when we measure median or mean latency values, the percentage of devices experiencing significant issues decreases, indicating that high latency is generally not sustained over time but occurs as spikes. Most users experience low latencies on average, but these spikes in maximum latency can still be problematic for applications requiring a consistent low latency connection. Therefore, efforts should be focused on improving the consistency of connectivity by addressing the causes of these maximum latency spikes.
All right, now our last test is on to latency to destination. All right, we measure latency to destination with ping tests. In a ping test, a packet of information is sent to a destination and then sent back to the sender. From this, the time that it takes for the packets to return and the percentage of packets that do not return can be measured. This round trip time will be a distribution of times. There is variation in time between the packets. Here we see the results of many ping tests. There are 55 devices, all located in Milwaukee. Each ran roughly 5,000 ping tests to 20 destinations, so that's 250 tests for each device destination pair. Each box plot represents the distribution of the mean round-trip times for that device destination pair. Again, so each box plot is a distribution of means. Decimation is indicated in the chart title. Each device is on the x-axis and ordered increasing median of mean round-trip time. The left plot is tests to Chicago. The right is to Johannesburg. South Africa is a lot farther from Milwaukee than Chicago is, so it makes sense that round-trip time tends to be much higher in the Johannesburg tests. It's almost a full order of magnitude difference. Also, the devices that have lower round-trip time for one destination tend to have lower round-trip time for other destinations. This also makes sense. Destinations of ping tests can also be specific websites, not just geographic locations. Here we see the results of ping tests to Google on the left and UChicago's website on the right. Higher round-trip time mean that users may have trouble accessing these sites. We tested many major websites, and we didn't find any extreme values or outliers here. All right, in conclusion, we wrote documentation for and conducted exploratory data analysis on newly collected Milwaukee data. We wrote reusable functions that generate a reproducible analytical report. In the future, our notebook can be used to produce reports for other cities that the IEI investigates, and these reports can be used by the IEI to identify areas of focus for improving internet affordability and accessibility. Thank you.